Yes, it started. Jeremy, we are online.
We are live. Well, welcome to I think we're the 10th TinyML4D show and tell, where we give students a chance to present what they're working on. Some of the presentations may be beginning with an idea and expecting to get some feedback from the observers. Other people are presenting fully done projects. We do try to concentrate on TinyML, where we're doing machine learning on tiny devices, but every once in a while we branch out to EdgeML with some of the bigger devices. And Marco isn't here today, but he might pop in at some point. So Marcelo and myself, Jeremy, are looking after today. Do you have anything to add, Marcelo? We've got the workshop.
Yeah. As I said before, I think people should be ready for our next workshop in May. The week of May 6th will be very interesting. And if someone has wants to present, we are still preparing of finalizing all the agenda. So we'll publish in the next days. Marco is not present today, as Jeremy said, because he's in China now with the people. We have a workshop there, ICTP workshop with the CD Studio people. It will be very interesting. They will talk about the TinyML there in that team spot that also speak Portuguese in China. So it's near Hong Kong. So it'll be interesting. But that's it. So I think that let's do it.
Yep. I think we can get going. Abdul's group, do you want to take over the screen?
Yes. Second. Yeah, is it visible?
I can hear, I can't see yet. Oh, there we go.
Okay, yes, it's starting. Yes.
Okay.
Good.
Hello, everyone. Sorry about that. Hello, everyone. My name is Saleh Al-Jabr. I am a student in computer science in King Faisal University. Today, me and my team, we will be presenting our project, Enhancing Poultry Health Management through TinyML, based analysis of bird sound. Here are the names of me and my team. My name is Saleh Al-Jabr, and I have with me is Abdul Aziz Al-Khays, Abdul Moshen Al-Khatib, and Rahman Al-Majid. And so we are supervised by Dr. Ali Zahrani and co-supervised by Dr. Ramasamy. Here are our SDG targets. We have 17 SDG targets, but mainly highlighted about 4 SDGs, which is zero hunger, good health and well-being, responsible consumption and production, and finally, life on land. Our main objective is to ensure the well-being of poultry for sustainable egg and meat production. And second objective is to activity classifications using bird sound, early warning for anomalies, and controlling the ambient environment. The activities that we considered is distress, drinking, feeding, and finally walking and clucking. So we have a recording of each of these activities that we have to consider in each of the objectives that we have. This is our architecture. So the neural network processors uses the list on the right, the microphone, NDIR sensor, and
sorry. I think it is not moving your presentation. It's not in presentation mode, I think. No? Yeah. Okay. No.
Is it visible now?
Yeah. If you put in presentation mode, it's better. No, it's bigger. It became bigger. No?
You can see it now. It's in presentation mode.
Okay. Okay.
Ah,
It doesn't appear for us. It appears the slides are appearing. That's the point.
Just 1 second. Okay, just check. Okay. Yeah. Okay, is it good now?
Is it starting? Yes. Thank you.
Sorry about that. So, like I said, this is the architecture. The neural network processor used the microphone, NDI sensor, and Nano 33 to get the activity, to get the information from the poultry farm, which is the humidity, the light, the temperature, feeding, and the fanning, to make sure to control it and make it better. Okay, and now Abdul Moshen, my friend Abdul Moshen will continue.
Hello, everyone. So for the process flow, we have collected data starting from June 2023 until now. For annotation, we have used Avian Researcher. And for pre-processing, we have used 2 techniques, filtering and windowing. For feature extraction, we have used DWT, spectrogram, and BSD. For agent post training, we have used 1D CNN and also 3 layers and 4 classes. And finally, inference and deployment. So for the result that we have got, the photo on the left represent the unfiltering result, which it gave 86.5% accuracy. And the one on the right, it's the filtering result after we filtered the result. And finally, Abdul Aziz will continue.
Hello, everyone. In conclusion, the neural network processor ensures bird health and farm productivity by combining the plurality sensors with the hens voices. We can create a monitoring system that will help us detect anomalies. Thank you. Also, these are a different data that we collected for the different accuracies. And these are the gases that we collected in summers. Sorry, it is in Arabic. But these are every row is average of 1 week for 8 weeks. This is the summer data, and these are the winter data for different gases and for the relative humidity and temperature. And thank you.
Okay.
Wow.
Great. I have a question. When you said you have you have sensors, you collect the data. You said you have the microphone for the sound, light sensor, correct? You talked about any NDIR sensor. I missed it. What means what this sensor is?
Yeah, non-destructive infrared sensor.
Okay, infrared.
Which is
so
from DF robot. The number is SEN0536. That's what the model that's what the sensor we have used.
Okay.
Which gives the temperature, humidity, along with carbon dioxide.
Mm-hmm.
These are the 3 data populated from that sensor.
Okay. Okay, explain it for me. It was not clear for me at the end. So, okay, you have the sensors, you got all those informations, and what the main purpose of that? The classification. It was not clear because it was very small, the presentation.
Yes, yes.
What the class?
Yeah.
Okay, perfect.
So now is my screen visible?
Yes, okay. It's possible to see.
So actually, there are so many activities we can take it from the sound, but the avian researcher, they have advised that the distress sound is very important, because
Okay.
sometimes actually in university we have a research center. It is very well maintained. There is no possibility of any predator to come inside.
Super.
But in the rural environment, there will be some kind of other predators will get enter into that boundary. So whenever it get distressed, that is the first priority you have to give. You have to announce that information to the stakeholder. So
Okay.
he told that you have to record the distress sound. So we created some kind of distress. Actually, it is a long process. Only at the last moment, last 1 month, we created the distress sound. We recorded that one. And also when the feeding, normally 5 o'clock early morning only, they will provide the feed. They will put 180 grams of feed per day, 90 grams in the morning, 90 grams in the evening, in order to get 120 grams of egg. That is what the metric they used to follow. So how much amount of drinking and feeding, what is, when it is taking food, what is the sound it is coming, what is that activity? This is the sound, very important. Then other times when it is doing resting or something or socializing, it will produce the clucking sound.
Mhm.
So this walking is not for the egg laying one. This is for the broiler meat production. It will be in a particular confined environment. It will be doing a walking at that time. It will be making some different sound. So these are all the 4 sounds we have taken. Actually, it is a bigger project. So first, what the student projects, what they have done is this one, activity classification using the bird sound. So they have collected all the sounds, and then now we have to tell whether this belongs to a distress or drinking or feeding or walking and clucking. So this they have done. That's what the initial phase. Now,
Okay.
after doing that one, we wanted to take all the sounds, and the avian researchers have given some library files. It is still under research. So what they have done now, when it is affected by flu or when it is having some other problem, how the sound is differing. Like that, they have given some label data. So now, first step is first, what is the activity is doing? In that activity, whether it is okay, good, or average, or it is below that particular threshold level, that we have to do. That work we are now doing. It is not the part of the students' work, but it is a research work. Then after doing that one, whether it is related to a particular environment, whether it is because of the excessive humidity, or it is because of the heat, or it is because of the ventilation. So actually we have got some of the breeder catalog. For each and every breeder catalog, for a particular species of that breed, what is that relative humidity for each and every month?
Okay.
June, July, like that, they have given some table. So now one can do a semi-automatic thing. For this month, I can put this light as this much, switching on, switching off the light, and humidity like that I can set. But suppose if you want a reactive behavior, then from this neural network processor, whether I want to adjust that particular humidity by switching on the humidifier. That's what they were doing at the walls. But this part is yet to be completed. This is a research project. It is not the students' work. So what they have done is only they have classified the activity based upon these 4 things. And the samples also, what they have taken is, we have collected a huge amount of samples, but then it is demonstrating samples for each category. That's what the students have done. But actually, in actual research, we have got 100 case of samples, 1 second samples.
Okay. There is a question from Dr. Lila here. She asked about, did you find that every sensor data is useful, and or can you do without any of the sensors? Because I understood that, of course, for this first phase, you only use the microphone, correct, or sound for the activity classification, but you have the other sensors that you use for the next phase. So far you think that all the data that came from those sensors will be important?
Yes, sir. Yes, sir. Because actually, still we have not presented every results. It's a part of that one. We have got the egg production per day. What is the egg it's producing per day? How much amount of feed is being given? All the data is available with us. Now we wanted to do a mapping, and we wanted to find out what is the controlled environment which will give the better productivity. That's what our objective. But still, we have not concluded with that one. But all the
Okay.
data are very important.
Okay.
Actually, the light data is not shown to you. People have suggested that we have got two kinds of environment. One is with the ordinary, the compact fluorescent lamp. The other one with the this incandescent lamp with the controlled thing. They will be varying the light amount. It will give some kind of heating, because the heat is very important. For some of the breed, it needs to be 75°F to 82°F. Then only the production is good. So we have got some kind of data. We are trying to figure it out, what kind of environment is good for this productivity.
Okay.
But we don't have the answer right the moment.
Okay, thank you. Thank you. Jeremy?
I'm quite interested about the second step, where you've got all that the compounds, the CO2. Where's the final? Oh, it was on a different slide.
Yeah, I will get into that one.
Yeah. Are you planning on using edge impulse and doing
already we have, yes sir, yes sir. See, for this one they have used the edge impulse only, but throughout the entire workflow we wanted to use only the edge impulse. These are all the results from edge impulse, but this is not the actually live classification. We did not show. It is the trained one, offline classification results only we have shown, because there is an issue. This ethics clearance, if you allow me just 1 minute, this ethics clearance was approved only in the March. This is the date. 6th of March only we got the ethics approval. So far how we were collecting the data is, we went with our computers and this NDIR sensor and multi-channel gas sensor and the microphone. Everything we used to go around nearer to that place, and we keep this thing at it's a rack, 5 column and then 6 rows. A cage. In each of the cage there is some 5 hens will be available. So we have got some 250 in one bay, another 250 on the another bay. So we were given a time of just 1 hour during the feeding time at the morning 6 o'clock. We went there, and at some other time also, whenever they give a permission, we used to go over there and we collected the data. But full collection of data is pending. Now we plan to put up the sensor on the rack continuously in a power down mode, and we know the activity. When there is an activity, now we come to a good conclusion. So at the time we will switch on and we will sample the data. So it's a long process. This project is given for 24 months, but before that we have started. Now we are on the right track to deploy the sensors at the actual poultry center.
Nice.
Okay, great.
Good
Jeremy,
luck with that.
I think it's time to see, you know, if you have a, I don't know if the second one is here, or we'll go to Thommas.
We've had a few more people join. Looking for James and Millicent. If anyone out there is from that crew. And if not, the last group, can you give up your screen?
Yes.
And,
thank you so much.
And congratulations, Ramasamy, and very good work. Congratulations.
Yeah, that one that just presented, that sensor fusion part is always a complex part if they're sticking with that impulse. I'm curious later on how they deal with that. That's a good presentation. So Marcelo, what's better here, for you to do the link with Thommas, or do you want me to?
No, I do here.
Okay, so this is from Brazil, Thommas, and I think he'll introduce himself. Can you do sound as well?
Yes.
Good morning. Hello, everyone. My name is Thommas Flores. I am PhD student of University Federal of Rio Grande do Norte. And today I would like to talk about advancing TinyMLOps, a robust model update in the Internet of Intelligent Vehicles. So my presentation is divided in 4 steps. First, I talk about the motivation, our purpose, results, and conclusions. Today, vehicles can have a wide range of sensors like speed sensors, chassis weight and torque angles, powertrain speed, pedal position, fuel level. In this way, the automotive industry utilizes this sensor to create a scenario using this data for data analytics and machine learning to provide to user with valuation information about the vehicle development. So, however, for this platform to be effective, vehicle data needs to send to a server. Typically, this server is a cloud server. So for this, have some possible risks. And the first is cybersecurity risks, privacy concern because you need to transmit the information for another place, and infrastructure costs because you need to high speed internet to send this data, and interoperability because you need constantly send the information to car from to the server and the server from the car. In this way, our purpose is create a pipeline and to update, and basically is a step by step to update the machine learning models embedded in vehicles diagnostic system and like in a device already to minimize the risk you mentioned earlier. So our purpose is divided in 4 parts. The first involves the collecting data and is a experimental study, and in data check and pre-processing, like remove outliers, not the numbers, and split the data in training and test data. So the second step is the related to training and validation of machine learning model. In 13 steps, we create the machine learning, tiny machine learning model is this convert process to TensorFlow model to C++, C++ model to go embedded in device system. So in finally and deploy, and this deploy we consider the monitor model and update. So here we have a first architecture. The data collection involves obtaining the two connections on the vehicles, and we connect the update to in vehicles and send the information by Bluetooth to the app torque, and is a app to connect to update devices, and this app create a CSV with the information about the different sensors of the vehicles, and in this CSV is uploaded to a personal computer, and in this personal computer we process the data and create the model. So for creating machine learning model, we use the Python and Colab for this, and we framework to create the model is the TensorFlow. Here has overview for this model, like answer the vehicle information is obtained. This data is processed to generate the model. We use the Python and Colab, and with the TensorFlow to create the model. The input of the model is the pressure, temperature, and speed of the car, and the output is to estimate the CO2 emission is a greenhouse parameter. So in the next step is the conversion process, where the TensorFlow model is converted to TensorFlow-like model with the using The post quantization is the quantization of the train. And before, after the TensorFlow Lite is converted to C++ to go to embedding a machine learning system. Here a general overview of the conversion process. We have the TensorFlow model. This TensorFlow model is converted to TensorFlow Lite. Inside to TensorFlow Lite, we have JSON. This JSON has the model structure, like the number of edges, layers, and bias. And after this structure is serializable to a binary number, and in this binary number is converted to a hexadecimal number to embed the machine learning system. To embed in low power device system, and we use the C++ language. Okay. In this case, in this study case, I use the Máquina A0 is OBD open source. The main model is a ESP, and for deploy the model, we use the Arduino platform. So to update the model is this overview communication sequence diagram, where each model parameter is transmitted to radio station to the OBD2. The protocol used is the ESP-NOW protocol. So the radio station queries the model version and send a message to OBD2. The OBD2 sends back the version. If the OBD2 version is lower than the radio station version, this transmitter is begin, and we compare the last model version to a new version in radio station. Okay, and in this case, the radio station from the size of new model to OBD2, and the OBD2 checks if is capable to storing the new version of the model. The OBD2 checks if there is an algo storage space available. If there is sufficient space, it information to radio station that's right to the update by creating a memory space to receive the new parameters and send the message to radio station, and I ready to update the model. So in this step, the radio station send to OBD2 model parameter in the U position in array with the hexadecimal numbers. So these steps repeat. Each model parameters and positions is transmitted one by one, and you have a confirm the action and transmit a new parameters and position. This repeat. And now I present some results. The first, we created two models, one with high accuracy or precision, another with a low accuracy. This is a new version model, and is a old version model. So we have update, comparison, prediction, performance before and after the update, highlighting the change information around time in 10 seconds. So in this case, the precision is very low. After the update the model, we have high accuracy in the precision of the model. So after this, we creating three arrows are intentionally inserted into the structure of the message to be transmitted. So the two first errors occur in the bias and the edges. So we result in changing the precision of the model, but but the inference was still possible. So the 13th error was inserted in the structure description. Like if you have in your structure the word like input and changing this word for another word. In this case, we modify the structure of the model. So in this case, the inference is not possible because the structure is broken. Sorry. Power, another result is the power and the latency to transmit the each parameters and to update the all model. So the first is the one represent the time to interval to each message. Or in this case, this message to go to from the radio station to OBD2, and we have this time and the Twitter this time. For the update all model, we consider this step, the A step to C step. We have this time to update and transmitted all model parameters and allocate the model parameters in OBD2 and check and confirmation. We have this time. So and have this power evaluation to radio station and this value. So when you receive or OBD2, we have 1 watt, and in this case the value is high because in the OBD2 we have the model update and transmitted and the inference and in parallel. However, so finally we have the memory evaluation, like the flash memory, and is this value in OBD2, and the memory RAM is this value in OBD2. So we need more memory compared to radio station because we need to reservation space, a memory space to a new model. We compare this value and this value. So conclusions. And in this case, we represent the energy efficiency and we reduce latency because with the TinyML in OBD system, we don't need to send any message to a cloud and waiting to response and privacy the same way, and we don't need the connection with the internet because, for example, you have a charge station for electrical vehicles. In this charge station, you put the radio station, use the charge station to update the model of the vehicles. We reduce networking overhead, resilience to network failure because you have the mechanism to confirm the send and receive the message and then stop the transmission. And if you recover the network, you continue to transmission new model and the low cost. Thank you so much. Is my email to any questions.
That was great, Thommas. I think Thommas just managed to join us.
Yeah.
Hey.
Great.
Really interesting presentation. Unfortunately, our volume was a little down, so we may have missed a couple of chunks there. I love those car sensors. I have both a Wi-Fi and a Bluetooth one. And so I'm really curious what you're doing. It almost seemed like you were doing a live update with information from the car. Is that correct?
Yeah, I'm transmitting. I'm using ESP22 to transmission to OBD2 in car.
And then do you generate a CSV file and update the TensorFlow model, or what's the process there?
Yeah, I'm creating a TensorFlow model for interpreting in ESP and transmit each parameters to another ESP and they create and update the model. So it's not like the federated learning because I'm not transmitting the each parameters like the bias and dualness. I'm transmitting all model architecture.
Wow.
No, great work, Thomas. Congratulations for you guys for the Federal University of Rio Grande do Norte.
Yeah.
From over Brazil. And give my regards to Ivanovic, Professor Ivanovic.
Yes, my professor.
We have a question there. Are you using the network to connect the station? Does that make sense, Thomas?
Yeah, I'm using Wi-Fi. It's a now protocol. It's like Wi-Fi protocol. Maybe the engines range to send the message 200 meters. Yeah, it's a LTE. LTE. Oh.
And your final sense of the process, is it something other people should be repeating, or is it like super complex and
No, it's complex, yeah, but it's so simple. I have a paper with the step-by-step implementation this. I can share the link here for another people can go and reply this work and have a GitHub with all codes for reply for share this work. It's no so complicated, but it's simple.
Does anyone out there have a question for Thomas? I feel like there are a lot of parameters you could use this for working with machine learning models. As I said, the sound wasn't so good. What were the main parameters you were working with?
In this case, I use an MLP, a very simple MLP to transmit H parameters. So in the process to convert the model, TensorFlow model for an interpreted model, you have converted a lot of parameters of TensorFlow for a simple array with these parameters. I share and send these parameters is not the TensorFlow parameters, is converted parameters. Like you want array with the hexadecimal numbers.
And by the way, Thomas, for example, when you do the training, you use the data for the training. You normalize your data, no, from the data from sensors.
Yeah.
To start the input tensor. Those parameters you also send when you have a new model. You also send the normalization parameters to be applied for the new sensors during the inference.
Yeah, normalization in the training and set a range operated range for new and another models is like challenging because the data is all the time changing. In this case, I set this physical value, range to physical value, and if normalization these my input parameters for these values.
Okay.
I share my the link with this paper.
Okay, thank you.
Do we have any questions for Thommas or for the first presentation? Anyone out there with any questions?
Okay. People are quiet today. No, but the good thing is, I think the presentations will be have been recorded. It will be available in our site and in the Harvard site also. So people, if they have questions, I think Thommas, we can send an email for Thommas, his email here, or for people from King Faisal University. So, great presentation, great projects. Thanks a lot. Thanks a lot, Thommas.
Thanks a lot.
Yeah, thank you, Thommas.
Thank you.
As far as I don't see that James or Millicent have joined us, so I think we're pretty close to done for today. Is there anyone out there have any questions or observations?
Okay.
Well, I think we're good then.
Okay, thanks a lot, guys. Put in your calendar, first week of May 6th, we'll have our virtual worldwide workshop. I think it'll be very interesting. And also pay attention to the ICTP website. We also will have a workshop in Brazil in July. It will be an in-person workshop. Everyone is invited to go there. This is in person, of course. So you need to enter your. I have a limit number of people, but we'll try to find some research to help with the travel, etc., and accommodations in São Paulo. I hope Thommas, you guys, and Professor Jovanovic can be present in São Paulo in July, and it'll be interesting. Okay, it will be an interesting workshop at TinyML together with IBM. IBM Brazil will also participate. Okay, thanks, guys.
Thank you so much.
Thank you, Marcelo and Jeremy, for hosting this meeting.
Thank you.
Well.